Negin Baghbanzadeh of New York University in Canada. Or to butcher that name, Canada. Please welcome.
Okay, thank you. Hi everyone, I'm Negin, and today I want to talk about our paper, Advancing Medical Representation Learning Through High Quality Data. Okay, so our objective is that we aim to train robust image and text encoders for medical data. One common way to do that is to use CLIP. CLIP uses an image and a text encoder and train them simultaneously using image caption per dataset. If you look at the datasets that have been used for training CLIP, we can see an increasing trend in the dataset size. We can also see the same trend in the medical data. There is an increasing trend in the dataset size. So our question here is that, is more data always better? To answer this question, we decided to curate our own high-quality dataset. Ideally, what we want for a high-quality dataset is that we want to have medical images with their corresponding report, like this. But having such dataset is very hard and it has its own limitations, and we really can't do it on a larger scale with on a variety of modalities. So what we can do here is that we can go and use the images and the figures and their captions in medical papers on PubMed Central, like this. So we can extract the figures and their corresponding caption, and also to enhance the captions more, we can also use the in-text references for each figure. So that's what we did basically, and this is an overview of our whole pipeline. First, we downloaded the papers on PubMed Central and extracted the figures and their corresponding caption and the in-text references. And let's look at how the data is at this stage. So for the figures are like this, and they're either single panel figures or they're compound images. And the compound images can be either all medical, or a combination of medical and non-medical, or they can be all non-medical. Next, for the captions can either be for a single image, or it can be a little bit more complicated and be for a compound image. And for the captions for a compound image, we can see that there was letters referring to each of the subfigures. And for the in-text references, for example, for this compound image, the in-text reference is either referring to some of the subfigures, or it is just like a general description about the whole figure. Now, for the next step of our pipeline, we filtered out the non-medical data out of these image caption pairs. Then we extracted the subfigures of the compound images using a Dutch model. Then we used GPT to extract the subcaptions from full captions. After that, we aligned each subfigure with its corresponding subcaption. After that, we needed to summarize the in-text references, and the reason for that is because the in-text references are usually very long, and in order to be able to train a text encoder on them, we need to summarize them. And lastly, we use GPT to assign a modality to each of the subfigures. And we consider three main modalities for our dataset: radiology, which can be X-ray images or ultrasound images. Next modality is microscopy, and the other modality is visible light photography. They can be like retina images or dermatology images. And after all of this, we have our curated high-quality dataset. So if we want to compare our dataset to previous work, as you can see, our dataset is much smaller than some of the previous work, like PMC15M and Biomedica, but our dataset is carefully curated. It has a higher quality, and it has all the listed properties here. So we started training using this dataset that we curated. We trained the CLIP model, and our training took 8 hours on 800 GPUs. And then after that, in order to compare the model trained on our dataset, we did some downstream tasks to see how it's performing compared to other models. The first downstream task is retrieval, and As you can see here, overall, our model is beating the models that were trained on significantly larger data sets, such as PMC, 15M, and Biomedica. And for the next downstream task, which is zero-shot classification, we can also see that, especially in radiology modality, our data set in size is much smaller than the other data sets, but it's getting better performance. And for microscopy and visible light photography, we're getting on par performance with the models that have been trained on much larger data sets. So after that, we also wanted to do a latent space comparison. We wanted to do this to make sure that the pre-processing steps that we added to curating this data set is really affecting in learning different representations for our data. And first we did a visualization, and as you can see here, our model is learning different representations compared to the previous models. And we also did an MND test to quantify this difference. Now, in order to see what makes our data set superior to the other data sets, we did some ablation studies. The first one is that we compared training a model on compound images versus single panel figures. And as you can see here, the model that was trained on subfigures is getting better performance than the model that was trained on compound images. So we can say that OpenPMC's superior performance is because of the quality of its figures. And also another ablation study that we did is that we wanted to see the effect of summarized in-text references in the learned representations. So we trained a model on only the captions, and another model that was captions and in-text references, and we can see the model that was trained with the summarized in-text references is getting overall a better performance. So we can say that incorporating the in-text summaries is enhancing the contextual knowledge of the model. So to wrap up my presentation, I want to talk about the significance and impact of our work. And I want to go back to the question that I had in the beginning. Is more data always better? We showed that data quality matters, and we showed that models that were trained on a smaller data set but curated with a higher quality can beat models that were trained on significantly larger data sets but were not carefully curated. For our future work, we would like to see the effect of using high-quality data curation on a larger scale. And for more information on our work, you can visit our Hugging Face and GitHub. Thank you.